All right, so we've talked about first order kinetics. We talked about the integrated rate law there, and let's continue with the integrated rate laws for second order and zeroth order kinetics. So again, the integrated rate laws are a way from going from the rate law, which we saw before, where the rate was equal to some constant of proportionality to some power of the reactants, to the integrated rate law, which says what's the concentration of things as a function of time. So let's take a look again at second order rate constants. So for second order rate constants, then again, the second order kinetics is the change of A as a function of T is equal to the reaction constant times the concentration of the reactant squared. Now we're dealing only with unimolecular second order reactants here because the math gets more complicated when there's both A and B. You end up getting a couple differential equations. We're just sticking with the simplest cases. Physical examples of this, gas phase reactions requiring two molecules to collide for the reaction to occur. This is a very common place where you get second order reactions because it's proportional to how much of these and how much of these there are. So an example in this case would be two molecules of hydroiodic acid reacting to produce a hydrogen gas and iodine gas. And so in that case, there's only one product, but it's a second, ends up being second order. Sorry, there's one reactant, but it's second order in that reactant. Okay. So that's the physical setup. Let's dive into the math now. So for second order kinetics, we get that the rate of disappearance of A dt, that is equal to the rate constant times A squared. So that is again a differential equation. You're trying to find a function where this relationship is true at every point along the function. We will not, again, solve it. This is not a differential equations class, but what you get out is that 1 over the concentration, and again, that's a function of time, is equal to kT plus 1 over the initial concentration. So this also is of the form of y equals mx plus b, right? Because our dependent variable, or independent variable is t, and if that's the case, then k times t is mx plus a constant 1 over the initial concentration. So y, so y equals mx plus b, where the dependent variable, the y that we plot, is 1 over concentration of A, and the intercept is 1 over concentration of A0. Here's a second order kinetics plot. We've got time in some arbitrary units over the concentration. So we have the first half-life, there's a large concentration, it's quite fast. And then if we look at the next half-life, then the amount of time it takes to go from A0 divided by 2 to A0 divided by 4, it's twice as long. Because if we've cut the concentration in half, that means the rate has been cut by a fourth. And in order to get rid of it, half of it there will take twice as long. And if you look at the next time period, again, it'll take 4 times as long for the half-life there. So that's what we're seeing, is that it starts out very fast and then it slows down at the end. That is sort of the characteristics of a second order reaction. Okay, example problem. Let's work this through. Nitrogen dioxide decomposes at 300 degrees C via second order process. We're given that at second order to produce nitrogen monoxide and oxygen according to the following chemical equation. A sample, and we don't really need to worry about the stoichiometry, right? It's a second order reaction. That's just there for decoration. We know that we have nitrogen dioxide decomposing, so we know what the species that we're interested in is, and we know what the rate law is. So a sample of NO2 is initially placed in a 2.5 liter reaction vessel at 300 degrees C. If the half-life and the rate constant at 300 degrees C are 11 seconds and 0.54 molarity inverse second inverse respectively, how many moles of NO2 were in the original sample? Well, we know what the integrated rate law is, right? We know that it's going to be 1 over A is equal to KT plus 1 over A0. So we could plug that in, but we can actually go straight to the half-life, right? We're given the half-life, so we can use the formula for the half-life we just worked out. That's probably going to be the fastest way. So T1 half, again, if we had plugged into this, we'd get the same answer in the end because we're essentially plugging in the half-life. But we already did that in the previous problem. Let's just skip to there. Is 1 over K, A0. Okay, so we're given the half-life, and we're given the rate constant. So all we need to do is solve for A0. So we multiply both sides by A0, the initial concentration, divide both of them by T1/2, and we get A0 is equal to 1 over K T1/2. All right, and so we've got all that information, right? It's 1 over K, which is 11 seconds, and T1/2, which is 0.54 inverse molar inverse seconds. And so plugging that in, that gives us, so the seconds cancel. We have 1 over inverse, I said meters, it's molar, it's capital M. We get 0.168 molar. So that was the initial concentration. But we're not done, right? We want the number of moles. So the number of moles will just be 1.168 moles per liter times 2.5 liters. That cancels, we get 0.421 moles. That's the number of moles of nitrogen dioxide we started out with. Okay, so that's how you handle second order integrated equations. Again, the process is relatively straightforward. You have an integrated rate law, which you can look up, and then you just plug in and do algebra.